Good morning. This presentation will cover cable capacity, sizing, and shock protection based on European standards. The presenters are myself, Abelardo Morales, and my colleague Daniel Ding. The agenda for this presentation consists of two sections. The first section is the conductor capacity and sizing of the phase conductor or of the line conductor as referred to by European standards. The second section is the electric shock protection and thermal sizing of the protective conductor, which will be presented by Daniel Ding. In the first section, we will be going over a brief overview of the standards and the different installation methods. We will also go over a short overview of current carrying capacity calculation concepts and the line conductor sizing constraints. We will then proceed onto the software user interface, in which we will use ETAP software to perform a sample current carrying capacity and line sizing calculation. Cable capacity standards. IEC 60364, British Standard 7671, and NFC 15100 are all applicable to low voltage installations. That is, installations with voltage levels less than or equal to 1 kV alternating current and less than or equal to 1.5 kV direct current. IEC 60502 is a medium voltage standard, and it's applicable to installation with voltages less than 35 kV. Lastly, IEC 60092 standard pertains to electrical installations in ships with voltage levels less than 15 kV. Cable installations. As it can be seen from the table, British Standard 7671, IEC 60364, IEC 60502, and NFC 15100 support a wide range of above-ground as well as underground cable installations. As previously mentioned, IEC 60092 supports only installations on ships. The current release of ETAP, which is ETAP 18.1.1, supports all of the installations supported by the standards mentioned in this list. Current carrying capacity. What is cable current carrying capacity? Current carrying capacity of a cable is essentially the consideration of the cable's thermal limits. It is necessary to determine the maximum current a conductor can carry under the conditions of use without exceeding its temperature rating. This is to ensure proper or normal cable operation. Why is current carrying capacity analysis needed? The reason is because cable manufacturers and standards provide base capacity values for a specific installation condition at particular base temperatures. However, these conditions differ from the actual installation of the cable out in the field. As a result, cable current capability calculations need to be performed in order to account for such differences. There are two different methods used for calculating the current carrying capability of a cable. The two most common used methods are the thermal analysis and tables method. However, in this presentation, we will only focus on the tables method, since all the standards covered in this presentation are based on such method. Thermal analysis method will be covered in a different presentation. Table-based method uses a correction factor concept in which the base capacity value is multiplied by all the applicable correction factors pertaining to the cable installation and operating conditions of the cable and its surrounding medium. Each standard provides a base capacity value based on the cable type and the specific installation type. Correction factors, which are used to account for the differences in the actual cable installation and base conditions, are also specified by the standard. Common correction factors include ambient temperature, soil thermal resistivity, and the grouping of a cable. Depending on the standard, other factors can also be applicable. Factors such as thermal insulation, depth of burial or lay, the circuit clearance, etc. In addition to the factors provided by the standard, ETAP also provides a user-defined factor, allowing the user to add additional derating to the current carrying capacity of the cable if necessary. Line conductor sizing constraints. Constraints to consider when performing line conductor sizing include, but are not limited to, loading, voltage drop, short circuit, overload, zero sequence, and triple harmonics. In this presentation, I will focus on loading, voltage drop, short circuit, and overload constraints only. Moving on to the software user interface. I will be using ETAP 18.1.1 to perform this sample calculation. In order to perform ampacity calculations, we first need to go to the cable editor and select a cable library. Since I want to perform capacity calculations based on low voltage standard, I will select a 1 kilovolt cable, metric unit system, 50 Hz frequency, copper conductor, 3 conductors per cable, and XLP insulation type. Now I will select Heesung as the source. I will select a 10 mm squared cable. I will then enter 60 meters as the cable length, which will be used when performing line sizing calculation. I will then go to the loading page to specify the loading of the cable, which will also be used for line sizing calculations. Notice there are 3 loading current options for the sizing of the conductor: operating current, full load of element, and user defined. Operating current. This is the operating current value automatically updated based on load flow results. The value can be updated by going to load flow mode, going to the study case. In the info page, under the update section, I would select the cable load amp option. I will then run load flow. Reopening the cable editor and going to the loading page, you can see that the value is updated from load flow. Full load of element. This is used to size the line conductor based on the full load current or rating of the selected device. You can select from buses, protected devices, transformers, motors, etc. User defined. If you have a particular loading current value for which you want to size your cable, you could go ahead and enter it here. For now, I will use the operating current value. Now I will go to the capacity page to calculate the derated capacity of this cable. In this page, you can select the standard you want to use to perform cable analysis. Notice the different standards available for this calculation. I would select IEC 6364 to perform capacity and line sizing calculations. Next, I will go ahead and select an installation type. Notice the wide range of installation types, from underground to above ground, as specified by the standard. For this example, I will be using underground buried installation. Next, I will select in conduit as the installation subtype. This particular installation type is classified as method D1 by IEC 6364. Notice the base capacity value of 58 amps is populated. This base capacity value corresponds to a base ambient temperature of 20 degrees Celsius, a base conductor temperature of 90 degrees Celsius, and a soil thermal resistivity of 250 degrees Celsius centimeter per watt, as defined by the base ampacity table provided by IEC 60364. The next step is to apply the applicable correction factors for the cable's actual operating conditions. Note that increasing the operating ambient temperature to 55 degrees Celsius and the soil thermal resistivity to 270 degrees Celsius centimeter per watt causes the derated ampacity to decrease from 58 amps to 40.5 amps. Increasing the ambient temperature and soil thermal resistivity contributes to the heating effect and slower heat dissipation of the cable. Next, it's the grouping section. Increasing the number of circuits from 1 to 5 will cause an additional reduction in the derated capacity value to 26.3 amps due to the fact that there are more cables and further contribute to the heating effect. Finally, applying a correction factor of 0.25 meters to the circuit clearance actually increases the derated capacity to 32.4 amps. This value aligns with the fact that the circuits are being spaced. Now, clicking on the correction factors button, we can see all the applicable correction factors being applied to this particular cable and its installation. Additional derating. As previously mentioned, an additional derating user-defined factor can be entered if necessary. I will select not to use this factor for now. At this point, the current carrying capacity analysis for this cable has been completed. The current carrying capability of this cable is 32.4 amps. Moving to the allowable capacity section, you can select from three options: derated, user-defined, and UGS calculated. As the name of this section implies, these options are used to specify the allowable capacity, which will be used for load flow alerts. Using the derated option sets the derated capacity determined from this analysis to be the maximum allowable current. If you have a particular maximum current limit, you can define it under user-defined. The last option is the UGS calculated. This value is the calculated capacity value or result from the underground raceway systems. In this example, I will use the derated option. By doing this, the displayed value, which is this one here, will be compared against the calculated value from load flow. In case the value calculated by load flow is greater than the allowable capacity value, an alert will be posted in the load flow alerts. I will now proceed on to the sizing phase page or sizing line conductor. Loading constraint. This is the loading current for which you want to size your cable. In this example, the value is based on the previous load flow calculated result. Maximum voltage drop. In this field, you can specify the maximum percent voltage drop requirement. ETAP also provides a maximum length. In this case, it lets the user know that this 10 millimeter squared cable can have a maximum length of 107.67 meters and still be within the 2% limit or constraint. I will now select to size my cable using short circuit and overload constraints. However, in this case, results are not provided. This is because the clearing time for short circuit protection and nominal current, IN, for overload protection have not been specified. To specify these parameters, I need to go to the protection page. Notice there's a short circuit current section. The max and min currents can be specified either as calculated or user-defined. Notice that they have been previously calculated in this example. These currents are automatically calculated and updated based on the short circuit results obtained from running update short circuit KA calculation from star protection and coordination module. Max KA values are updated based on maximum short circuit current or user-defined C-factor options. The minimum KA values are updated when minimum short circuit current options or option is selected in the standard page of the Star Mode Study Case Editor. You can also define current values by simply selecting the user-defined value and entering the values here. For now, I will use the existing calculated currents. In the Protected Device section, you can select protected devices. For overload, you will need to select a protected device which will be providing overload protection to this cable. Notice that there are three options. Selecting none will not allow you to perform line sizing based on overload constraint. Selecting user-defined will allow you to manually enter the nominal current, IN, and operating current, I2, of the overload device. Selecting device ID will provide you with a list of protected devices connected near the cable. I will go ahead and select Fuse Main, which is connected upstream of the cable. Now, doing so will automatically determine IN and I2 based on the fuse time clearing curve. Similar concept applies when selecting the overcurrent device. Selecting device ID and fuse main will automatically determine the clearing time for line protection. Based on the short circuit current and time clearing curve pertaining to the selected device, in this case pertaining to fuse main. Now switching to the sizing phase page, it can be seen that short circuit and overload results are available. A minimum cable size of 10 mm² is required to withstand a fault current of 13.81 kA and a clearing time of 0.01 seconds. Finally, for the selected fuse having a nominal current of 50 amps, a minimum cable size of 25 mm should be used to satisfy the overload constraint. In the results section, ETAP provides a summary of the line sizing calculation results. Based on all the constraints being considered here, the optimal cable size suggested to meet all the cable requirements in this particular analysis is one conductor per phase of size 25 mm². Such cable will have a current carrying capacity of 54 amps and a 0.44% voltage drop. As it can be seen from this calculation, the overload condition is the determining factor for which the cable size needs to be increased. Without this constraint, a 10 mm² cable is suitable. However, with this requirement, the cable needs to be increased to 25 mm². I can go ahead and click on the select button for the optimal size. Notice that ETAP automatically updates the cable size to 25 mm² and updates the number of conductors per phase to 1, which is defined in the info page of the cable editor. Now going back to the sizing phase, we have completed our capacity and line sizing calculation results based on IEC 6364. At this point, I am done with the first section of the presentation, and I will now hand over the presentation to Daniel Ting, which will be covering the second part. Thank you.
Good morning. My name is Daniel Ting. We will proceed with protective earth-thin conductor sizing capability within ETAP. Including in this webinar, we will focus on engineering capabilities in terms of short-circuit thermal sizing for PE conductor as well as electric shock protections for low-voltage systems. ETAP provides the capabilities to define various grounding types such as TNC, TNS, TNCS, TT, IT collective, individuals, and groups. You can open up Transformer Editor, go to Grounding page, and change earthing type or grounding type. You can also define grounding types at other low voltage source such as the generator, the grid, PV inverter, wind turbine generators, etc. ETAP allows users to configure multiple core cable, armored, sheath, and auxiliary cable as PE conductor. In this webinar, we will also cover the integrations of cable sizing with short circuit and protection analysis, determinations of protection disconnection time based on protective device curve, and the flexibility on user-definable values. The PE sizing process can be simply described using flowchart below. Step 1 and 2 include setting up PE conductor, defining upstream protective device, and running short circuit analysis so that the disconnection time of protective device can be calculated. These assume grounding types already been defined at upstream transformer or source. Then, ETAP provides capability to assess maximum short-circuit thermal energy imposed on PE conductors. At the same time, the minimum loop current, loop impedance, disconnect time, and touch voltage are calculated for electric shock protection. When they fulfill the required size or permissible values, then the PE sizing is completed. Otherwise, change cable size or protection device settings until all criteria satisfactorily met. Now, if we simply open up a cable and go to configuration page, you can see cable information from the library. And you notice that this is a 4-core cable. 3 core for the phase, the 4th core for PE. You can change and use the 4th core as neutral and add an auxiliary cables as PE. If we move on to the cable next to it, you can see this cable contains 3 times 50 square mil core and 3 times 10 square mil core within one single cable. This can be set up in ETAP cable library where you can have different conductor size within same cable. Again, you can customize your cable conductors as neutral or PE. After completed step 1, we move on to step 2. You simply need to run short circuit analysis in star mode. The calculated short circuit currents will be transferred to cable editor. You can find the short circuit currents under protection page of your cable editor. You also have the options to user define your design short circuit current for future proving. Next, you can define your protective device. ETAP automatically detects upstream circuit breaker. Using the short circuit current and protection tripping curve information from the library, ETAP is able to determine device disconnection time. Again, you have the options to user define disconnection time or simply select one of the built-in fields and MCB according to the standard. After setting up, we proceed to thermal sizing under Sizing for PE page. The maximum ground fault and disconnection time stated are obtained from previous analysis and setup. ETAP calculates lateral energy and the required conductor size either based on formulas or tables values defined by the standard. In this case, the existing PE cable met the required size criteria. On the next tab, you have electric shock protection page. You can find earthing type stated here, which is defined at the source or transformer in this case. ETAP calculates loop impedance, which taken into account PE conductor impedance and also ZE loop impedance for low voltage grid element. Loop current, disconnection time, and touch voltage are also calculated and shown here. Next to the calculated values, you have the permissible values. You have options to change touch voltage permissible standard or include local ground resistance to assess the impact on touch voltage. On the next cable, you can see that the calculated values did not meet the criteria. The calculated values are shown in pink color alert. ETAP Cable Manager allow user to manage and change multiple cable size and types, as well as have an overview of multiple cable sizing and alerts. You can select your cable and circuit breaker and plot protection's time current curve. You're able to see your cable damage curve, your protection device curve, your PE calculated loop current and the permissible limits, as well as the maximum short circuit currents. You're able to select different cable thermal damage standard and shows I2T curve in the plot. I can switch to the ground mode and include my phase conductors, neutral and PE conductors within the same plot. With this, I'd like to end the presentations and thank you everyone for attending.